So patterns and relationships between physical observables. So this is what we're going to look at. So by the end of the lesson, and we're going to look at a couple of different examples of this. So students should be able to investigate patterns and relationships between physical observables. So physical observables are just things that we can look at, and we can make observations and we can measure, and then we can look at patterns between these physically observable phenomena. So the first idea that we're going to look at here is what's known as Hooke's law. So Hooke's law basically is if you take a spring, so you take a spring like this, and what happens is when you add a weight, for example, or if you add a force to the spring, what's going to happen is that that spring is going to extend. So if you take a spring, there's two, if you add a force, so force, so remember a force basically can cause an object to move, can cause an object to change shape, change direction, speed up or slow down. So they're the things that a force does. And we measure force in newtons. We use this symbol N for Newton, so to measure force. So what are the things that can happen when if we add a force, apply a force to a spring? So we can get extension. So we can get extension and we can get compression. And this is like fairly obvious. So if we take, for example, we take a spring like this, if we apply force in this direction, what's going to happen is the spring will compress. Okay, so you're kind of like squeezing up the spring. But if we attach for a weight, for example, and apply force to the end of the spring, you're going to get what's known as extension. And this happens in a particular way. So there's a particular pattern that happens, that's called, and there's a law around it as well. So a force, as the force increases, the spring gets longer by equal amounts each time. So what we can say is, so imagine if we have a graph like this, and if we say, let's say along the bottom here we have extension, just abbreviated with E. So this is my x-axis and this is my y-axis. And then along here we have, let's say, the force. So the force in newtons. And we continue adding, let's say, we keep increasing the number of newtons that we're adding, and what do we actually observe? What actually starts to happen? Well, what will happen is we will get this predictable pattern. So we will. So what will happen is the extension will happen like in a uniform way. So you'll get like this straight line like this. Okay, so it'll as you apply force, it extends by a certain number of centimeters. As you extend more force, it extends by another amount of centimeters. And what happens is it extends in this uniform pattern. So you get this like what's called a straight line. So what we can say then is that these two, so the extension and the force that's been applied, are proportional to each other. So we can see here in this diagram, it represents that. So for example, we start off with no extension on the spring. We add a force, okay, so we get an extension of x. Then if we add 2 times that force, we get twice the extension. If we add 3 times the force, we get 3 times the extension, 4 times the force, 4 times the extension, etc. And if you graph it, you get a graph that looks something like this. So as the force increases, so as we add on more force, the spring gets longer by equal amounts each time. So this is a pattern that we can physically observe, and we can plot, and we can measure. So this observation, or this pattern, is what's called Hooke's law. So the extension is proportional to the force applied, provided the limit of proportionality is not exceeded. So that means that each spring has this proportionality constant. In other words, it can only stretch so far. And then once it goes past that limit of proportionality, what will happen is the spring it'll bend out of shape and it won't go back to its original shape. So what we can say then is that the force is equal to k times the extension. We just call the extension E. So force is k times the extension E, and this k here is the proportionality constant. Okay, so or just constant. So this proportionality constant, so different springs will have different proportionality constants. So it depends on, for example, how much force they can take and how much they can extend. And this is what's known as a proportionality constant. And this is unique to each different individual spring. So so this might be the pattern that you see with one spring with a particular proportionality constant. Then if you try a different spring, it might have a different proportionality constant. So you could get something like that. And then if you have another spring, you could get another pattern that looks kind of something like that. So all of these values here, all of these springs will have their individual what's called their proportionality constant. So they could extend by a certain amount depending on like what their proportionality constant is. So this is what's known as Hooke's law, and this is an experiment that we will do in the lab, and we'll have a look at this and you'll see how it works, and we'll also construct graphs like this as well. And this is a pattern that you can observe, and you can like look at this pattern and look at the relationship between the force being applied and the extension on the spring. So generally, when you analyze it, you get something that's like this. Okay, so along the bottom you have, for example, weight in newtons, or the force that's applied, and then you have the extension, for example, in centimeters. And generally you get this type of setup here. So you get this proportionality, like as one value goes up, as the weight increases, the extension increases. And it goes up until a point, and then to a certain point then you get no more extension. Okay, so you've got to the max of your spring. Okay, so it's not going to extend anymore. And if you keep adding mass to it, what will happen is it'll extend, and it will get to the point it might end up like looking something like this. So as the downward force increases, the extension of the spring increases, proportionality, and at a certain point the maximum extension of the spring will be reached and it will stop extending. And at this point the spring may become damaged and not return to its original shape. So that's what happens. So when you reach this k constant, or this proportionality constant, the spring will bend out of shape and you won't get it back into shape. But if we think about the learning outcome, like what we're looking at, students should be able to investigate patterns and relationships between physical observables. So this is an example of a pattern and a relationship. So you get this proportionality relationship between the force applied and the extension on the spring. So just to look at some other examples, so obvious connections between variables. So it brings in this idea of what are called variables. So you have what's known as the independent variable and you have the dependent variable. So the independent variable is generally the thing that's changed. Okay, so what we change. And generally we put the independent variable on the y-axis when we're plotting a graph. So for example, in this experiment, the independent variable is y. Okay, so the independent variable is the thing that we change, the thing that we have control of. And then the thing that we measure is what's known as the dependent variable. It is dependent on the independent variable. So generally when we don't know exactly what we're going to get for the dependent variable, so this is what we're going to measure. So in this experiment, for example, when we'll do this experiment, the thing that you're controlling is the weight that you're adding on to the spring. So you have control over that. The thing that you're going to measure then is you're going to measure the extension of the spring. So in this case, so the independent variable, the thing that you control, okay, is going to be the force or the weight that you add on. The dependent variable is going to be the thing that you measure, which in this case is going to be the extension. Okay, so how much it extends. So that is what's known as the independent variable and the dependent variable. So here are other examples of these what are known as proportionality graphs. So we can see that one variable is proportional to the other. You get this nice kind of straight line. So other kind of proportionality variables or observables between phenomena. So if you take, for example, your weight on the Earth in relation to your weight on the moon. So if you were to plot those two against each other, so for example, your weight on the Earth in pounds and the weight on the moon in pounds, what you will get is you will get this directly proportional relationship between the two. So for example, as you increase by 6, for example, it increases the exact same amount each time between one variable and the other variable. Another one is hiking distance. So for example, the distance that you hike. So for example, the amount of time you spend hiking is proportional to the distance that you're going to cover. So again, if you were to plot these two against each other, what you'll get is you'll get this nice kind of straight line. And also then as well, if you rent out a canoe, for example, you will also get this. So the amount of time, the number of hours that you spend using the canoe, and the amount of money that you have to spend, to rent a canoe as well. So these are what are known as proportionality graphs, and these are patterns that you will observe again and again and again, when you compare certain physical phenomena with each other. And this is just one example as well. So Hooke's law, and we have looked at the relationship between the force applied and the extension of the spring, and that relationship is described in Hooke's law. So the extension is proportional to the force applied, provided the limit of proportionality is not exceeded. Okay, thank you for listening.